All right, here we go. Kia ora koutou, ko Douglas Walker, tōku ingoa. We're here this morning with Jenny Pollock. Jenny Pollock's past president of NZASE, the New Zealand Association for Science Educators, and she's also long-serving past president of Earth and Space Science Educators for New Zealand. And so Jenny has spent a lot of her time in education, both in the classroom and then trying to support Earth and Space Science education across Aotearoa. So Jenny's going to lead us through Level 2 Earth and Space Standards this morning. And as ever, if you've got any questions, please do just put them in chat. And I'll do my best to either interrupt Jenny if they're time sensitive. Otherwise, I might just hold them back towards the end and give Jenny a chance to answer all of the questions towards the end of the presentation, because I understand there is quite a lot of material to get through. You'll be able to watch this back again in the days ahead, and there are links to resources that Jenny has very kindly shared in the description, so it might be useful if you've got those open to access. Thank you not only to Jenny but also to Study It for helping to sponsor these webinars, and without further ado, over to you, Jenny. Ka pai, thank you.
Right. Kia ora, everyone. I'm called Jenny Pollock, tōku ingoa, and I'm going to start off by doing the first hour. I'm going to do extreme Earth events, a standard that covers extreme Earth events, and then we're going to be looking at the stars and planet tree formation and life cycles in the second one. So first of all, I'm actually going to share a PowerPoint. And so just give us a minute while I do that, and we'll go to share screen. And get to this one, and then we'll do presentation. Presentation, there it goes. Right. So this PowerPoint does a summary of the key points of extreme Earth events, and obviously at this stage of the exam, just being in a day or two, I can't teach it right from the beginning or anything like that. There are plenty of resources online that you can actually use for your revision, but this is just going over key points, and so there may be some things that I don't go over quite as well, but other points that I cover really well. So just have a look at this first slide, and this is actually making sure that with extreme Earth events you don't forget gravity. So when you are writing a question about anything, if you think about it with volcanoes, any eruption, of course, ash, lava, that sort of thing, is subject to gravity. If there are any landslides caused by tsunamis or underwater avalanches caused by tsunamis, it is gravity that is helping the material come rapidly downwards. If you're also talking about earthquakes in the land, instability, the results of that, gravity is also important there. So don't forget gravity. You might find that that is something that actually is able to bump your answer up to another grade if you're mentioning that as well. Okay, now just put a little bit about the Earth system here because it is actually in the standard, although it's very rarely strongly as part of the assessment, but you never quite know what you might get one year. So just make sure that you realise that the Earth system consists of four main parts: the atmosphere, which is the air; geosphere, which of course your rocks, your land; hydrosphere, which is water anywhere; and the biosphere, all living organisms wherever they live. I'll just go back to atmosphere. Atmosphere is air anywhere as well. So it could be actually bubbles of air deep in the ground, or as part of magma or something like that. Okay, and these things all work together. And so therefore, if you have a landslide, you might have trees that were growing on the land. They actually get cut down, which destabilizes the land. The land starts to move, particularly if there is an earthquake, and particularly if there is water. So already you've got life and the geosphere, and you've got the hydrosphere, the water, all working together to create something. Okay, so to make an event happen. So let's carry on with this. Okay, these 4 parts interact continuously. A change in one results in a change in another. Now, I'm not going to read every single bit of these slides, but that diagram that I have, that example that I've given you, is on the bottom of the slide. Now, first of all, just be aware of the Earth's layers, and be aware that the deeper you go in the Earth, the hotter you're going to get, and that what's important, particularly when we're doing this topic, is what is happening in the crust and what is actually happening in the upper mantle. But for now, it gets hotter as you go towards the centre of the Earth. Okay, and that there are great, enormous convection currents that occur in the mantle and actually in the crust, although that's not showing that here. And these are what are actually moving the tectonic plates. And this is actually showing that tectonic plates move apart, although you don't particularly need to know about this in any detail for this standard. But also what you do need to know is that the plates, as they move apart, they interact with other tectonic plates, and here they show subduction, but they don't always do subduction. There can be mountain building as well. Right. Okay, and this is just very quick diagram showing you the different plates, and we are affected by the Pacific plate and the Australian plate, which is over to the left of the diagram. And we are one of the very few countries where a tectonic plate goes right through us. Okay, now this is a very important part. There are 2 kinds of crust. Oceanic crust, young, dense, basalt rock. Thin, right? All those bits you need to know. Continental crust, made mostly of less dense and buoyant granites. Thicker, around about 40 kilometres, give or take. Okay, 2 kinds of crust. Now notice a tectonic plate can have both oceanic and continental crust. It can have both. And you need to kind of get that around your head. This is very important facts. Okay, now this is quite an important diagram also to understand. This is actually showing land. This is actually showing the grey is actually the land that is above the sea, and everything else is below the sea. The red colour is quite shallow, and notice that kind of hugs the land, and that forms what is known as the continental shelf. That's incredibly important when it comes to tsunamis. Also, the deepest part is the Kermadec Trench, which is the purple part right at the top hand right of the diagram. This is purple because it is just so deep. You can put something like about 3 Mount Cooks, Mount Aorangi, one on top of the other into that trench. It is so deep. Now, this map also, the orange, yellow, and red tends to be the continental shelf. The blue and the sort of tealy colour is particularly the oceanic crust. There are transition areas represented by other colours, but you don't have to worry about them at all. Notice that the continental crust actually, particularly finishes at where about Kaikoura is in the Kaikoura Canyon, which we talk about later, so that the oceanic crust comes right sort of down to Wellington and into Kaikoura, and which is part of the reason why you actually get whales there. So just get a sense of what is continental crust and what is oceanic crust there. Now, this shows a tectonic plate boundary, and you usually get a diagram these days that shows a tectonic plate boundary. I think it's pretty important that you should be able to draw it, but please note it comes down the Kermadec Trench, it comes down the coast of Gisborne and Napier there. It doesn't cut through the land near Wellington before at all. It goes below and it enters the South Island round about Kaikoura, and it leaves the South Island at about Milford Sound and then goes straight down again. Now, you've all heard of the Alpine Fault. That is a huge, great fault line along which you can have major earthquakes, but it's also part of the tectonic plate boundary. And on the right-hand side, you have the Pacific Plate, and the left-hand side, the Australian Plate. Note that the Pacific Plate is actually in the South Island, is mostly, is mostly continental crust. In the North Island, I'm sorry, I've just lost my train of thought of what I'm doing there. Notice that the Pacific Plate, is oceanic when it's off the North Island, but it is continental when it's part of the South Island. And the same with the Australian Plate is oceanic crust off round about Fiordland, and it's continental crust for the rest of the time. And these plates, the Pacific Plate, move at about 3 to 6 centimetres a year. And what is really important about these plates, and important when it comes to earthquakes, that these plates are moving all the time. They're moving and distorting the land and putting stress on the land as they go, whether they're under the ocean or on the land. And that's a pretty important part for when we get to earthquakes. Right, here is actually a very good diagram to look at. It shows you where, what is happening in different parts of New Zealand. On the right, Pacific Plate subducting under the Australian Plate. It's actually the continental Pacific Plate under the oceanic crust of the Pacific Plate subducting under the continental crust of the Australian Plate. And that is very clear on a diagram that is coming up. Go whiz down to the bottom of bottom left, and there you'll see that the oceanic part of the Australian Plate is subducting under the continental Pacific. It's going the opposite way. Okay, that's important because it kind of means that you've got this huge, great force of the Pacific Plate subducting up north, huge, great force of the Australian Plate subducting down south. That really twists New Zealand and is part of creating some of the major fault lines that you get. Now, another part to notice. In the South Island, the Pacific and the Australian plates collide and slide, mostly. Lateral and vertical movement along the Alpine Fault. There's no subduction there. That is continental crust colliding with continental crust. And more about that in a minute. Okay, colliding plates. If oceanic, and this is just pretty much doing what I've just said, but down the bottom there, oceanic crust diving under continental crust is called subduction. Oceanic crust can also subduct under oceanic crust. But note, if continental crust meets continental, then you actually get mountain building, which is what the Southern Alps have come from. So just be aware that when the plates collide together, they're not just subducting, they can also form mountains as well. Okay, and that shows slipping plates happening along the Alpine Fault. Right, this is also another very nice diagram, which I'm not going to talk about for too long, but it does show two very good cross-sections where you get subduction of Pacific Plate under the Australian Plate, and then down below, subduction of the Australian Plate under the Pacific Plate. It also gives an idea of how the plates are moving, and notice that the Pacific Plate slightly sort of changes direction as it's sliding down the Alpine Fault. Right, now this is also an important diagram because it shows you where there's oceanic crust and continental crust, and it's pretty much what I've just gone over. Be aware that land is pretty well always continental crust, and in terms of this standard, it is continental crust. There are little bits of oceanic crust, very old oceanic crust in different parts of New Zealand, but it's mostly continental crust. So be aware of that. So you can actually have a look at that and just remember in your head where the different subduction is happening. I will just go quickly. Notice the very top one, subduction of the PP under the AP. That, of course, is oceanic crust under oceanic crust. That is exactly the same down where the Pusica Trench is, if you notice that. Come down a bit further, oceanic crust under continental, round about Lake Pegasus, all that part of the country. Exactly the same actually happens in Fiordland, except the plates have switched around. In between, you've got continental, sliding past continental, and some vertical movement that is forming the Southern Alps. Right, and these are key places to know. I'm not going to go over those, but it's really worth putting a little bit of time into knowing it, because then when you meet a term in an exam, you're not having to kind of waste time actually thinking about, oh my goodness, where is the Alpine Fold? Where is the Kermadec Trench? You already know it. Questions often do give you hints or even label stuff, but it is still worth knowing. It really does save you time. Okay, now first of all, I'm going to go over volcanoes, and I'm going to try not to take too much time because this is an awfully long section. A volcano is a vent above a magma chamber that erupts lava. That is true of subduction volcanoes. It's not quite the same for Auckland volcanoes, but we'll be going through that. Right. Just be aware that an active volcano is like Mount Ruapehu, which could erupt at any time. A dormant volcano, e.g. Mount Taranaki, is one that is not erupting but will still erupt. And notice that an active volcano and a dormant volcano still have magma changes beneath them, which means that magma can come up from very deep where it's been made, and it can sit in the magma chamber until there's enough there to sort of cause an eruption. An extinct volcano has an empty or no magma chamber underneath it. At the time of the Christchurch earthquakes, people were very worried that the Banks Peninsula volcanoes, which are right near Christchurch, would actually erupt again, but they never would, because there is no magma chamber and no magma there any longer. So that's what an extinct volcano is. Sometimes you'll get a question about volcanoes that are more recent, as it were, and sometimes you'll get it about older volcanoes that are extinct, but you have to apply the knowledge that you know for the more active volcanoes to that. And there are some question ideas. There are some, all the exam papers from just about ever are in the folder that you will go into for your resources. Right, and here's a good general direction of the products of a volcanic eruption. And you are often asked about the effects of the eruption, not just the actual volcano and type of magma that is erupting. Note that magma under the ground is liquid. Magma under the ground is called magma. When it erupts above the ground, it's actually called lava. There are many different things that can come out of an eruption, and I'm going to show you some of those in actually picture form now. So there are lava flows. Pyroclastic flows are the scary ones that you don't want to ever get in the way of. Flows that actually hug the ground and sort of go for a long way. Tephra, fragments of rocks, and lahars, the kind of things that can actually sweep away bridges and cause terrible destruction down from an actual eruption. And lahars can actually happen well after an eruption too. Because of there's continual kind of wearing away of, say, the edge of a crater. Explain more about that in a minute. Okay, top picture shows you very hot lava. This is actually in the Hawaiian Islands, in the big Hawaiian Island, but this is what a lot of Auckland lava would look like as well. Runny and flows for a long time. It's basalt, and it takes a long time to cool down, so it can run a long way. Volcanic ash, that's Mount Ruapehu erupting. Notice how it's gone up into the atmosphere and it's spreading out, And of course, any planes flying will not be able to go through that ash cloud. They'd be able to go around the other side of the mountain, but you wouldn't be able to go through an ash cloud. Pyroclastic flows, as I said, the scary ones. This is a mountain erupting, and part of that ash going up has collapsed to form a very fast-moving pyroclastic flow. And the bottom picture is actually Mount Tarawera, actually having buried whole villages, and a little bit like New Zealand's got its own Pompeii and Herculaneum, but not to quite the same extent. But we still had people die and villages being buried. Okay, the effects of eruption of volcanic collapse. And this is White Island, which of course has been White Island Whakaari, which of course has been in the news for other sad reasons, also for steam eruptions as well. And apologies for not having this dated, brought up to date with that. In fact, when I finish this talk, I may actually put in a slide because of that. But what actually also happened with White Island, at some stage there has been a very violent eruption, and the whole side of the crater has collapsed, and those bits of rock that you can actually see out in the sea are actually parts of the collapse. That would have actually caused quite a massive tsunami that would have possibly affected the Bay of Islands, but it happened a long time ago. The worrying thing about Whakaari White Island these days is the very sad eruption that happened a few years ago in which people died, was that it was actually a steam eruption, a bit like a geyser on steroids, a bit like the geysers you get in the Taupo volcanic zone, but it was much more vigorous than that. And they come without any warning. There's usually when there's going to be eruptions, magma is arising from underneath the ground, and it is causing tremors that can be picked up in seismometers, and these can be seen to be getting stronger and stronger, and we get warning of an eruption. With these eruptions, the one that happened on White Island and one that happened on Tongariro, which I think I do have a picture in this, they come without warning, and so they're much more worrying in that way. Okay, now there's Lake Taupo, the crater lake on Ruapehu below, a full crater lake 2 months before the Tangiwai disaster. And the Tangiwai disaster, of course, and I can remember that being an older person, was one of New Zealand's worst. A whole lot of the crater lake kind of collapsed, causing a laha, took out the bridge. Now there's actually warning systems. And here is the same thing where in 2007, you'll see up the top, that is Ruapehu, kind of with nothing happened with the crater lake. You can see the crater lake there. And then down below there is a laha actually went. The warning systems worked. And the bridge, which would have been built super strong, that stayed intact. Cars were stopped either side of it until the laha had gone under the bridge and the bridge been checked. And so nothing happened this time that affected human life or even particularly farm life either. Okay, now the effects of eruptions carrying on, you can actually have gases that will actually come up, and certainly people in Ruapehu, gosh, sorry about that, in Rotorua, if they go and swim in the baths there, in the hot baths, they are told not to be in a small room, enclosed room, because you can get a lethal build-up of gases that are toxic. Okay, now magma. This is a key point. Please make sure you know the kind of next 2 or 3 slides. Molten rock rising from deep within the ground. Magma can erupt gently or explosively, and in between, what's really important is the amount of silica in the magma. The more there is, the stickier or more viscous it is. If you can't remember viscous, remember sticky, but if you can remember viscous, that's good too. The amount of silica can depend on the amount of silica sediments abducted and or the depth of the continental crust the magma travels through to get through the surface. the next 2 or 3 slides are really quite crucial. I'll keep moving on though. Types of different magma and the amount of silica, the viscosity, the temperature, the amount of gas, and the eruption style. This is a table you should know. And this is a table that there is always an earthquakes question, a volcanoes question, and a tsunamis question. In the volcanoes question, you are bound to be asked about the type of magma. And so you need to know this. You need to understand the relationship between the type of magma and the volcano shape. And you need to know the relationship between the amount of silica and the stickiness or viscosity. Notice that the less silica, the hotter it is, the more it can flow, the higher the amount of silica, very sticky, not quite so hot, but can trap enormous amounts of gas. Because it's a bit like hokey pokey, if you've ever made hokey pokey at school, which expands very quickly when the gas starts coming from the sodium hydrogen carbonate, and that's very much what happens in a volcano too. Okay. Subduction volcanoes mostly erupt andesitic or rhyolitic magma, so that's why subduction volcanoes have got a cone shape or a dome shape, or calderas, which we'll get to in a minute. The volcanoes around Auckland erupt basalt magma. Types of eruptions. There's Narahori erupting, which actually shows the ash cloud going up the pyroclastic flow. The one on the right is when you have hot magma, and this is what would happen in the Auckland volcanic field, coming up under a water source such as a lake or ocean. So those are just different types of eruptions, different types of tephra. You can actually have a look at these. Now, there are 2 types of volcanoes in New Zealand, subduction volcanoes and hotspots. Now, Auckland has got the active hotspot. There are other areas in the country where the hotspots have gone cold, and there are remnants of the volcanoes formed from that, and very occasionally you get a question about that. But you may also get a question about the Auckland volcanic field, which has got about 50 little volcanoes, and there may very well be another eruption one day. Right, I've gone over that. I'm not going over it again. I'm not going over that again. I'm not going over that again. And so I've talked a lot about oceanic and continental crust, so don't worry about this. Formation of subduction volcanoes. Now, the next 2 or 3 slides step you through this from the kind of very simple, if that's all you can handle, or going through to where it's more uncomplicated. Now, subduction volcanoes are formed when the oceanic crust of the Pacific plate dives under the Australian plate, assisted by gravity. There's that G word again. As the Pacific plate subducts, it gets warmer. At a certain depth, the plate becomes hot enough for magma to form. Now, a lot of people will put about the fact that the friction of the plate forms the magma. If it was friction, you'd be getting magma formed all the way along where the plate subducts, but that doesn't happen. So this is just the beginning. At this point, you are learning that the plate boundary gets warmer as it subducts, and it's got to subduct a reasonable way down for magma to form. Okay, so notice in this diagram, there's your plate subducting, and when you actually get to a certain depth, that is when magma will form. And the wet sediment that has subducted with the oceanic crust actually surprisingly helps with this. And there's another side that explains that. So magma is forming where you get these kind of blobby bits. The bigger blob above it shows where the magma kind of pools before it actually goes up further. So, carrying on. Now, make sure you know this slide. Water-laden sediments are subduction. Pacific plate being subducted gets warmer the more deeply it's subducted. When it gets to a certain depth, the water becomes superheating, and this actually literally breaks up the rock and that it's under and lowers the melting point of the overriding Australian plate, melting it. That is the formation of magma. not friction, right? You could mention friction if you want to, but you've got to mention this as well. The melted rock forms magma. It's hot. It's going to expand. It's less dense. It's going to rise up through the surface to cracks in the crust. It might stop halfway or most of the way up and sit in the magma chamber for a while, but it slowly moves up. Eventually, it erupts out of volcanic vents or cracks in the Earth's crust. And that is a subduction volcano. That's a really important slide to know. Right, now what makes volcanic eruptions explosive? And this is also important. So when magma is formed deep down, gases such as water, CO2, and sulfur gases, which is what causes the smells you get in the top of volcanic zone, are dissolved in it. A bit like carbon dioxide in soft drinks. When you've got the bottle, you haven't shaken it up, or you don't actually see the bubbles. Right. As the magma rises, because it is hotter and less dense and it's rising, the gases start to come out of that solution and start to form tiny bubbles. These expand as the magma rises, making magma even less dense, so the magma arises further. Really sticky magma traps these bubbles so they can't escape, and this puts pressure on the ground above, cracking it. Magma rushes up these cracks and their bubbles expand so much that an explosive eruption occurs. Now, andesite magma is less sticky, so less gas will be trapped. It's an explosive eruption, but you can watch it from about, a few kilometres away, usually without being in any particular danger or from a reasonable distance. The very sticky rhyolite magma you don't want to be within 100 kilometres of, because they are so explosive because of this trapped gas expanding and eventually kind of bursting out. Okay, now that is a diagram which I'm not going to run because of time. Taupo volcanic zone. Taupo volcanic zone consists of hydrothermal areas, and that's where you've got your geysers and that sort of thing, which is kind of what also caused the Whaikari White Island eruption and the one on Tongariro. Also got volcanoes, and these are cone volcanoes, and it's also got what's known as calderas, which form most of the lakes. And that's another one. Now, this is actually showing if you cut through the crust in the area of the Taupo volcanic zone, this is what you're going to find. Now, I'm not going to go over something I've already gone over, but just be aware as the Pacific plate goes down, it's also stretching the continental crust a bit. And that actually helps make the volcanoes more violent, because the magma, as you can see, ponds up underneath this kind of thinning area, and then it's got less distance to travel. Now, notice when we come to earthquakes, the Edgecombe earthquake, which is in one of the exam questions I'm going to recommend that you look at, that is also came about because the Earth actually is being stretched. So just remember that, particularly those of you who are maybe aiming for excellence at that. This slide is important. Three main types of volcanoes: cones, and there's a beautiful picture of Ngauruhoe, calderos like Lake Taupo, and then domes, and the domes and this is a very good picture image showing the domes on Mount Tarawera. And these are made from when there has been a more violent eruption and all the gas has been got off in this eruption. There's still a whole lot of magma to come up, and they literally come up like squeezing toothpaste out of a tube, and they just stick right up like that. Okay, this goes over cone volcanoes. Notice that there's layers of lava and layers of ash in a cone volcano. These are kind of an intermediate sort of violence. The magma is kind of intermediate amount of heat and amount of silica in it. Okay, and I just simply don't have time to go over this, but I will show you pictures Notice that Tongariro, Narahoi, and Ruapehu are in a line, and that is because it actually matches with the fact that the subducting plate is also in a line. That means that when the plate subducts down, there's actually a whole kind of line of volcanoes because it has to get to a certain depth for the magma to be formed. So that's what this is showing you. You can read the stuff about Ruapehu, notice the crater lake, and also showing a picture from 1945 that's showing no crater lake but a lava dome that is actually coming up. Taupo erupting and Mount Narahoi, and what's important about this is you can actually see the lava flows on the left-hand picture. The right-hand one shows you an ash cloud, but it also shows you a collapsing ash cloud, which is actually the pyroclastic flow. There's Tongariro erupting in 2012, and that, if you remember, was I told you that was a like geysers erupting, a hydrothermal. Sorry, I just lost the words there for a minute. And I will go back and actually add this into the slide after I've finished and put it online and replace the old one. So if you are, it's always a really good idea when you're coming to look in folders and Drive to always refresh your screen. And it means that if someone has changed something in the time since it was first put on, it means that your machine updates to the up-to-date work. Okay, Mount Taranaki, that's got a satellite dome there, and you can see the eruptions. There's an awful lot of lahars comes from Mount Taranaki, and you can actually see the smoothed out ground all around it. Okay, caldera and dome volcanoes. These form, and I've really got to flick through, and this is how violent eruptions form calderas. Is very well explained there, and there are some diagrams that really well. And notice the kind of, remember, this is magma that is expanding because it's got so many gas bubbles. It puts huge pressure on the ground, lots of cracks. The magma may only come out of one or two cracks, but the instability is still there. And so when the eruption is stopped and the magma chamber is empty, it all kind of falls back in on itself. And then over time, from rivers and rainfall and that sort of thing, you'll get the lake. Okay, carrying on. Taupo erupts. We don't want Taupo to erupt. It doesn't a huge amount of ash, and these diagrams are just showing that. And road cuttings, it is also showing layers of ash. And right, dome volcanoes. Mount Wanganui is also a dome volcano. It's just a little bit more eroded from a lot of human use. And there's the Tarawera one I've already showed you. And I'm going to quickly flick through these Kermadec volcanoes because there was a question on them one year. North of New Zealand, there are volcanoes that are quite big. They're all underwater. This is showing oceanic crust subducting under oceanic crust. Notice the blue up the top. That shows the sea over all of it. And you're getting volcanoes and lines again. And you can see where there's been eruptions, caldera collapse, new volcanic cones coming out of that. Despite there being subduction down in the South Island, there's only one little, quite old volcano. The subduction is relatively new, and it also dives down very deeply, and probably quite quickly. So there may simply not be time, or the steepness of the dive means you don't get any lava formed. Okay, here's geothermal systems. Make sure you know about these because not only are the geothermal systems, but this can also cause these geothermal eruptions that we're talking about. Okay, right, and this can also happen under the sea, and these are called black smokers. That's the effect of the Earth system on volcanic eruptions. You can actually read through that when you come to this. Auckland Volcanic Field, I won't be able to spend too much on this either. This is showing you a good comparison. Pretty important that you realise that the Auckland volcanoes are all small as compared with the South Island ones, And I've got a red line down the bottom. That's a red line that shows the extent of the cone of the Mount Eden. But if you look at that red line, that only just fits into the crater lake. So effectively, you could put Mount Eden in the crater lake. So make sure you've got the difference in size there in your head. And know this page. This talks about the plume. Now, it's not subduction here. You've got stretching of the crust, which helps this process, but no subduction. You've got magma coming from very, very deep down, and it's very hot, and it hasn't got a lot of water in it. Okay, so it comes up. That is the consequences of not only the formation plus what can actually happen. You can read through that. Now, there are two main types of eruptions, basically one that comes up underwater and one that doesn't. Okay, phreatomagma, these ones, the ones that come up underwater can form these lovely little lakes. And if you see in Mangere here, the example in Mangere, you've got something that has been formed by from the water coming up under a lake, and then you've also got a cone, which is the water coming up under land. And, of course, another cone is Mount Eden, One Tree Hill, that sort of thing. Okay, now this is where you get, if you get lava, you're going to get this lava that just flows forever, and that's why Rangitoto is actually that shape, because it has been formed from that lava that just flows out. Rangitoto did actually have about 2 or 3 stages of eruptions, which is why you've got that gentle sloping, but you've also got what looks like a scoria cone on top. Okay, you can read through that and just, right. Earthquakes, I'm only going to, there's some very important points in here, and then I want to spend hopefully a good 5 to 10 minutes on tsunamis, because that's often the questions that get done worst, and I think it's because they're so often left to the end after we're doing all the other stuff. Earthquakes can be formed from volcanic activity. I've talked about that. It means as the magma rises, you're going to get shaking, and which seismometers will pick up. And as you get further, as the magma gets further up, it's obviously going to cause more shaking or greater intensity, and that is how you will know that there is an eruption coming. And this has been continually monitored around New Zealand all the time. We have many earthquakes because we straddle a tectonic plate boundary. Now, remember what I said here about the slow and continual movement of the plates every year. And these are diagrams that you're familiar with by now. And be aware that we have got a lot of faults, and there's a lot of faults offshore as well as onshore. And an offshore fault moving can also cause a tsunami. Okay, this is actually just showing some of the faults, and I'll flick over that. Now, how faults form. And don't necessarily confuse faults with the tectonic plate boundary, even though there is an alpine fault that goes along that. Notice, this is a pretty important slide. The PP and the AP are converging slowly and moving slowly past each other all the time. The crust is distorting and stress. This builds up and sometimes is released by huge cracks in the crust. These cracks are the fault lines. These fault lines kind of stick together as the plates keep on moving, slowly creeping, moving, distorting, stressing. And every now and then that the sides are kind of being jammed together, and there's a whole lot of elastic potential energy being built up. And every now and again that will give, which is called the breaking of a fault line, and that will actually cause an earthquake. And you can get breaking that way or breaking that way. Faults only move infrequently. The plates are moving all the time. Faults only move infrequently, sometimes just every million years or thousands of years or whatever. Faults can also be close to the tectonic plate boundary or far away. They can be a few metres long, or they can be as long as 1,000 kilometres, which is the Alpine fault is just about 1,000 kilometres. That's really important to get into your head, that stuff. Okay, now when faults break, they break underground, they break at the focus, the break kind of runs out from there, seismic waves come out, And the ones that reach the surface first, that is called the epicenter of an earthquake. And of course, that's where the seismometers are. And so that's where they get measured. Okay, so know the difference between the focus and the epicenter. Here's the Christchurch earthquake showing the Greendale fault. And if you've got a minute, it's worth following that link because it actually shows you the phenomenal amount of aftershocks afterwards. Now, faults build up elastic potential energy over time. More elastic potential energy, a stronger earthquake. The shallower the earthquake, the stronger the shaking we're going to feel on the ground. After the initial shaking, aftershocks may occur as the land kind of settles back, and not necessarily along that fault line, but elsewhere. Okay, now this is what's known as a normal fault, and you need to know the difference between the next 3 slides I'm going to show you. A normal fault is when land slumps down, and this is showing you the Edgecombe earthquake, and you can see the difference in the land. And the land has fallen down and actually stretched a bit, so you've almost kind of created a bit more surface land. A strike slip is when you get sideways movement, and the Christchurch, the Greendale earthquake was effectively that. There was a little bit of upward movement, but mostly that way. So that's a strike slip. A reverse fault is when the land goes up, and an awful lot of New Zealand, the South Island faults, and all the faults going up from Wellington and up sort of to the East Cape, those you will pretty well always get reverse faults. Okay, where the land, because the land is being squeezed, remember the Pacific plate's pushing in, land is being squeezed, so the land shoots up like that. Where the land is being stretched, you'll get slumping of the land. Where it's just sliding past each other, you'll get the strike slip faults. So know the difference between a normal, a reverse, and a strike slip fault. You often get given the diagram these days, but you may actually have to label it. And this is just showing some pictures of faults. And this one you can actually see by just following, say, the slim grey line, you can actually see how the different faults have kind of moved the different layers of rocks. And those, of course, are very old layers of rocks that were probably formed many millions of years ago. Earthquakes can also happen actually at the subduction zone as well, because the Pacific plate isn't hot yet, so it's cold and brittle and it cracks. So now there's actually different earthquakes, so I'm not going to spend too long on those. Notice that earthquakes can be deep and shallow and along the Alpine fault because there's no subduction, so there's no deep earthquakes. They're all shallow, which is part of the reason why an Alpine fault earthquake would be very serious and cause quite a lot of damage because it's all very shallow. Okay, and this shows cross-section of, you can have a look at that yourself. Shallow earthquakes occur everywhere, even along the Alpine fault. This talks about the different sorts of seismic waves. P waves come first and are the fastest. S waves are second and are slower. The P and the S waves can go right through the earth, so it can be picked up by seismometers on the other side of the earth from where the earthquake might have happened. The last two are the strongest, but they go along the surface and they cause an awful lot of damage. Okay, and that's just showing one. Seismographs, they record seismic waves, you can read through that. And this is how you actually find out where an earthquake's epicenter is. And you do need to know the difference between the Richter scale and the modified Mercalli scale. The Richter scale measures the magnitude of an earthquake, the amount of energy it releases, whatever type of earthquake. The modified Mercalli gives an indication of the actual impact of an earthquake and is based on people's experience. So it wouldn't have been able to tell you much about a fieldland earthquake or an earthquake that actually happens under the sea because there's no people there to record it. Okay, now this goes through a lot of historical earthquakes. I don't have time to go over them, but if you read through those, there's good pictures there. It is worth reading through these past ones because, one, you might get asked about one, or two, there'd be information you can apply to whatever situation we're actually given. Right, quite a few of those there. And also I know about liquefaction as well. Right, so let's get to, there's an awful lot of earthquake stuff. even the Kaikoura one. Okay, it does mention mega thrust earthquakes. They're pretty sad things and rather scary things. There was a question on it one year, so hopefully you won't get another one. Tsunamis. Okay, I'm just noticing the time, and I haven't got very long. There was a question in a paper a couple of years ago or a year ago which said that there'd only been one person ever killed in a tsunami in New Zealand. That's actually not accurate, and I want to actually correct that because 300 Ngāti Koata people in my area were killed from a tsunami about 500 years ago, and I want to just give respect to those people. Okay, so, and just be aware that that low, there has been, New Zealand has got a history of tsunamis. There's plenty of evidence of tsunamis, and that we can get tsunamis that actually happen in New Zealand, or we can be affected from tsunamis that actually come over the right across the Pacific Ocean from Chile, and there are questions on that. And there's the one I'm concerned about. Tsunami is also recorded in Maori oral tradition, and it talks about D'Urville Island. Okay. Tsunamis displace water, however it happens. And I'm going to go over the ways that they can be. But the most important thing is it actually displaces water. You can read the rest of that later, but don't just think that tsunamis are caused by huge earthquakes underwater. They can be, and they're immense and destructive and kill an enormous amount of life. But also an equally destructive one could just be a landslide going into a lake, or a huge block of ice falling off the end of a glacier and swamping a lake and making the lake water slush over into a village next door or something like that. Okay, and I would know a little bit about waves, and notice that they're different from wind waves. Wind waves is just the surface of the water moving. With tsunamis, it's the whole water body that is moving, whether it's a lake or whether it's an ocean, whatever. So the water just keeps on coming and keeps on coming and keeps on coming. And so this is a really good diagram showing how the tsunami actually moves up over can just keep going and going and going. And because the tsunamis have got a crest to them and then a trough in them, if the trough actually happens to hit the coast, that's particularly when you get the water rushing out. And that, of course, is one of New Zealand's, how we're now taught if we ever see water rushing out, particularly if it is accompanied by a strong or a long earthquake, you get the heck out of there. Don't think you're looking stupid. You won't be. Just go. Okay. Right. And there's a cross-section of the coast during a tsunami, and notice that tsunami waves out at sea can have this enormous wavelength. As they get to the ocean shore floor, the ocean shore, as it's shallowing, is actually slowing down the wave, and that wavelength has to go somewhere, and it goes into height. So that's when you get a tsunami wave won't do, it'll just rock a boat slightly. That's all it'll do out at sea. As soon as it gets to the shore, it becomes massively destructive. They can also be generated on the other side of the earthquake, of the Pacific. And Chatham Islands has been particularly hit, in New Zealand. So there's quite a few that over the years has actually come from Chile. Okay, I've talked about offshore faults and I've talked about water displaced. Just be aware that any fault movement underwater, if you just get sideways movement, it's not going to cause a tsunami. It's not displacing water. Might do other stuff. The shaking might shake sediment off a canyon or something like that, but that in itself won't cause a tsunami. Water's got to move, the fault line's got to move that way, which would be a reverse, or it's got to move that way, which would be a normal fault. That displaces water. Okay, so now there's a whole lot of examples. Here's a reverse fault, right? Here's offshore subduction, the slow distortion of a plate, which then actually flicks back. That's another way. Tsunamis can be generated by volcanic eruptions, and I think I showed some of them. A landslide going into a lake or a bay, a pyroclastic flow entering a lake or bay, or a river, damming a river. The collapse White Island again for Kari White Island, a collapse of a crater, and there's a diagram below there too. Any of these underwater volcanoes, particularly if there's been a violent eruption and a caldera collapse, could cause a tsunami. And there's a diagram of that. Landslides, there's a fjordland one where a landslide went into a fjordland and actually caused quite a bit of rocking. My husband was down there in a boat, and he definitely actually felt it. And the tsunami wave reached 4 to 5 metres on the other side of the fjord. If that had happened where there was a lot of people living around there, there would have been definite damage. Okay, we're surrounded by continental shelf that can collapse. Tsunamis can be generated from the collapse of the actual side or from the accumulation of sediment on the side, which then gets shaken by the earthquake and collapses. And a lot of sediment, which has come actually off the Southern Alps and come down rivers, gets accumulated in Kaikoura. And of course, we had that huge Kaikoura eruption. We were very lucky there was a tsunami, but we didn't get a major one for 3 reasons. 1, the tide was low. 2, the land dropped instead of rose up. And it was such a massive slump of sediment that it actually ground out to the bottom of the canyon, which meant that the water all went lower. But there was definitely a tsunami, and it was recorded by some CTV. Okay, that's it for that. So I'll stop sharing and see if there's any questions.
Thank you so much, Jenny. No questions at the moment, although I would like to just point out that I love the slides. Some awesome images in there and some key information in a nice, concise format. Do you want a wee break before launching into the next one?
No, I'm saying, actually, no, perhaps I will. I'll also actually I will modify one of those slides to show the geothermal eruption, because it's twice it's happened in New Zealand in very recent history. And also, I did have a whole lot of questions that I might have gone over if I'd had time, but as you can see, you have to fly through that material. I'll just be about 2 minutes, and I'll
if you don't mind, we've got one question you might be able to clear up very quickly for us.
Yeah.
Is the geology exam 3 hours?
No, it's only what you're allowed 1 hour, but usually people are only sitting 1 exam or 2 exams, and that's 3-hour time. So it probably means you've got more than 1 hour to spend on your paper. I don't think there's very few people will be doing all 3 externals, and that's why I never go over the 3rd one, because so few people are doing it. But hopefully you will have more than an hour. You'll be allowed to stay in the room for 3 hours. Sorry?
This student says that their school is only allowing them an hour for the geology exam, which seems unlikely given that it's an NZQA exam. So normally NZQA would stipulate the time of the exam, and to my knowledge that was 3 hours. But I hope that helps Mars Kid, who has asked that question. And we look at the timetable and just put any other answer in chat if I can find it. But certainly for other exams, no matter how many papers you're sitting, you have the full exam time available to you.
Yeah, and I'm sorry if you're not having it, but hopefully you will have it. You should be able to go into that room and stay there for the whole 3 hours if you want to. Yeah.
Great question. Thank you for asking it.
Very good question.
For a break, so we're just going to mute the microphone and the camera, and then Jenny will pop back on in a minute. If you've got any more questions, please do throw them into chat. Thank you.
Right. Oh, well. I'm back, Doug.
Thanks, Jenny. Yep, you're all good to go.
Yep. Oh, hang on. No, I've just put the. I'll just close down the extreme earth events. Just give us 2 seconds. Right. Okay, I'm ready to go.
Over to you. I'm happy to share and launch into it. Thanks, Jenny.
Okay, welcome back, everybody. And we're now going to be going over the stars and planetary systems revision. The same as last time. There's quite a lot to go over. Please put questions into the chat, as Doug indicated. And I did have some idea of some questions for you to look at. All the papers from a long time ago, as I mentioned before, are actually in the folders, the revision folders that you've been given access to. And I'll also put in there a document with questions that I actually had up ready to show you, but just didn't have the time. So I will put that in a document in the Drive folder so that you can actually see, one in the Extreme Earth Events, one in the Stars and Planets, so that you can see the ideas. Oh, excuse me, I'm just going to have a sip of water. So that you can actually see suggested questions that are good for you to have a look at. It's always worth looking at past questions, and at this stage probably not doing them, but maybe having a look at the assessment schedule as well. Just be aware that the assessment schedule has got everything in there that a student might write, but you don't feel pressure that you actually have to write that much. It is just to help the marker to cover a wide range of possible answers. Okay, now I'm going to share my screen. Here we go. Right, and hopefully you can all see that okay.
Yep, that's
okay, is that okay?
Yep, looking good.
Yep. Right, so let's go on here. Now, this isn't quite so long as the one before in terms of what there is to cover, but it's the same thing. You often get the topic about planetary formation is at the end and often ends up being rushed through because of time. I'll try and allow a reasonable amount of time for that. Okay. The first thing is, what are stars? I'll go over this because there's some important kind of what we call conventions there, and also helps understanding a heck of a lot. So a star is a massive luminous ball of heated gas held together by gravity. They born, live, and die. The mass is very important, and because if you're actually talking about actual mass, you would be talking at numbers that are just too unwieldy to deal with. The things we are familiar are used. So our sun, which is a bog standard, ordinary, middle of the pack star, is 1 solar mass, or 1 M sun. So that is where, if you see anything to do with mass and they talk about a 5 mass star or a 0.5 mass star, you have in your head, you relate it to the sun is 1 mass. So 5 mass is going to be bigger. 10 mass is going to be a lot bigger. 0.5, you're getting down in the really small stars. Okay, star mass can range from 0.1, which are your little red red giants and even your brown dwarfs, to 30 sun masses, which is your huge, enormous stars, which can go to massive supernovas. When we look out in the sky, we're only seeing the brightest. Even when it's completely dark, we're only seeing the brightest star. Okay, stars are also different colours. Now, that's all important, and there'll be some more conventions as we go on too, so just get aware of that. Right, there's two main sections in a star. This is really important for understanding the evolution, the life of stars. A hot, dense core where nuclear fission occurs, and like in the sun at the moment, we've actually got hydrogen. Sorry, I just have to move something. Right, two atomic. Yeah, at the moment we have actually hydrogen fusing in our in the core of our sun to form helium, and this results in the most enormous amount of energy that is released. Right, so you've got a hot, dense core. Now, a lot of things happen in this core as we go on with stars, so just remember that. Then you get an outer shell, okay, outer gas shell, and in a generalized star like our star, it's going to be hydrogen and helium, but it can be other elements as well. This outer shell is actually moving heat from the core to the surface. They have a balance between gravity pulling atoms into the centre and the pressure of heat and light radiating out. So important, those things. Measuring distance, again, that they're so vast that we need to have different measuring scales. Within the solar system, astronomical units are used, and that is the distance or the average distance from the Earth to the Sun, and it's rounded up as 150 million kilometres. So again, it is much easier to visualise if you know that that a planet like Venus, which is closer to the Sun, say I think it's 0.7 AU, then you get a sense of what it is relative to our planet. And Mercury, of course, is even smaller. Jupiter, of course, is much, much bigger. So, sorry, I wasn't talking about size there. I was talking about distance. So it means that Venus is much closer to the Sun. Jupiter is much further away. Sorry about that. Okay. So there we are. Jupiter is 5.2 astronomical units. You can immediately see we're 1, it's 5.2, it's much, much further away. Beyond the solar system, light years away. Light travels that fast, 300,000 kilometres per second. So you can just imagine how much it travels in a light year. But to be able to understand distance beyond our solar system, we need to use light years, because even astronomical units would very quickly become a very unwieldy number. So light years are used, and these are for distance. Better make sure that we're talking about it right. Okay. Right. That's a light year. Now, you wouldn't like to be jolly well saying 9.5 times 10 to the 12 all the time, or even writing that down. Much easier to say light year. Now, a few more things. That luminosity is the amount of energy a star radiates per second. And guess what? We compare it to the sun. So 1 L sun, that's the amount of luminosity that the sun gives off. And again, it's another measure so that you find it easier to visualize, get concepts in your head. Apparent magnitude, how bright a star appears to us from Earth, which is quite different from absolute magnitude, which is actually how bright it is. So, for example, Sirius, the brightest star that we see at the moment, it actually rises up over the horizon sort of in the early evening, and in the middle of the night at the moment it's pretty well up above. It's the brightest star, but it's actually really quite small. It has the greatest apparent magnitude, but Canopus, which is the second brightest, but its absolute brightness is greater because it's much further away. If you were to put the two together, then you would actually see that Canopus is much brighter. If you just imagine someone with a torch as opposed to a really bright light, if someone with a torch is standing right next to you and someone with a really bright searchlight is 100 metres away, it's going to seem like the torchlight is brighter. You put the two together and you can see that the searchlight is way brighter. Okay, now temperatures of stars. This is another thing again. I think if you actually, by mistake, say Celsius, it's not going to be the end of the world, but it's good if you can understand Kelvin. Colour of a star relates to its temperature. That is such an important point, and is measured in Kelvin. Now, there is such a thing called absolute zero, and certainly nobody on Earth has managed to create a temperature that is below absolute zero. They've gone within millions, billions of a degree of that, a degree Celsius, but they have not managed to get to it. Now, Kelvin is measured just in K, whereas we usually say degrees Celsius when we're just talking about regular old temperature on Earth, and possibly even the surface of the sun and that sort of thing. But if you're measuring anywhere else in the solar system, you need to be using Kelvin. Okay, so have a look. Comparison between Celsius and Kelvin, absolute zero in Celsius, minus 273, Kelvin, naught. Freezing point of water in Celsius, naught. In Kelvin, it's 273. Boiling point of water, 100. Kelvin, 373. Now, you'd never talk about temperature on Earth in Kelvin, because it's we know there's a heck of a difference for us between 0 degrees Celsius, freezing point of water, and 273. I mean, water would just be evaporated away. It wouldn't even be in the pot any longer. That means a heck of a lot to us. But if you're talking about the surface of the sun or the temperature of the middle of a star, that's such a, it doesn't matter whether you, the temperatures are irrelevant as to whether you're using Kelvin or Celsius, and so Kelvin is the usual one that is used. Okay, so the colours of stars. Notice that the surface temperatures in stars and colour and related, and this is kind of a little bit of a different concept that we tend to think of red, and that is a hot colour, and blue as a cool colour in just regular life when you're looking at clothes or something like that. But in actual fact, in the old days when people had open fires, or you had a fire outside in the paddock and you'd put a red hot metal poker in it, the poker would start to heat up and be red, but as it got hotter and hotter and hotter, it would actually go white. And the closest we have to that now is kind of light dimmers. If you turn a light dimmer on or a ray box in lab at school, you'll get a red and then an orange colour, and then you'll get white. You won't get blue. It won't go that hot. So you need to get a different concept of colours and temperature in your head, where blue is the hottest and red is the coolest. And there's quite a difference, and it's in Celsius here. It's quite a difference in temperature. Right, there is a relationship between spectra and temperature. And so the spectrum is actually when you're actually breaking up, white light with and I've forgotten the name. I'll remember that in a minute, unless Doug can give it to me. Prism. Remembered it, yeah. Okay, spectral, when you're breaking up white light with a prism, it breaks up into the colours, into different colours, and we usually call these the rainbow colours. But there are 7 different spectral classes. I'm not going to spend time going into this. If you find this tricky, just to remember O, B, A, F, G, K, M, don't worry too much about it. You're always given a HR diagram, and it would usually have the different spectral classes. What's most important actually is that you're remembering colour. The hottest stars are blue. The coolest stars are red. Okay, and here's the light spectra. You can read that. The spread, but what actually happens is that a spectrum of each star reveals dark lines called absorption lines. These are really pretty clever because absorption lines show which elements and molecules make up a star. And it's like a barcode. It's completely like a barcode. The barcode can be read, letting us know the elements and molecules the star's made of. That's what hydrogen looks like. The sun has got a whole lot of spectral things, and when analysed, you can see there the different elements that it's got. Spectra, funnily enough, can be used to find colour, composition, age of a star. It can tell you an enormous amount of a star. There are 3 different types of spectra: continuous white light emission spectra, which I'm hoping that you've seen in the lab and been able to do an experiment on that, which is from hot gas, and then from cold gas, you get kind of like the mirror image of it. So instead of a black line in an absorption spectrum, you've got a coloured line in an emission spectrum. But from this, you can actually tell an enormous amount. Doppler shifters for extension only. I've never seen a Doppler question. Those of you who have got the brain space, look it up and learn it if you want to. That's explaining it there. Okay, now the HR diagram. The HR diagram is very much like the periodic table. The periodic table helps us to understand the elements, but we don't dig up the ground and actually find the periodic table all neatly set out. So looking up in the sky, we're not looking at an HR diagram, but it's a way of understanding different types of stars. Now, on it, I've plotted the x-axis and the y-axis, and you really have to make sure you look at your HR diagram and identify what is on the x-axis and what is on the y-axis. And I'm going to show you some diagrams because there's pretty well always a question on an HR diagram that involves you knowing about the HR diagram, a question on the life cycle of the star and life and death of a star, and then something to do with the formation of planets or moons. Those are the 3 questions that you will get. Okay. So the HR diagram can tell us the following information. It could tell us a heck of a lot about a star, all those things, and I will show you. So here is a good HR diagram. Now notice here you've got temperature, and it's in Kelvin here, and here you've got luminosity. Okay, and notice it's an L sun. So if we go across from 1 to the middle of the diagram, we'd be actually finding the middle of the main sequence, we'd actually be finding the sun. Now the main sequence, that is shown as a, notice on the main sequence that the colours go from red all the way through to orange, yellow, white, blue, blue. But these main sequence are all fusing hydrogen to helium. And don't say burn, it's not burning hydrogen. It's a completely different process. Say fuse. Just remember fuse if you don't understand fusion. It's fusing hydrogen to helium. Other things are going on in white dwarfs. Other things are going on in blue giants and red supergiants. But the main sequence, they're all burning hydrogen to helium. Okay, so there you've got your x-axis in a regular way and your y-axis in a regular way. And I think I've got on the side here, you always take careful notice on the axes. Temperature and spectral class are always the axes, but that may be found at the top or bottom of the diagram. Luminosity and absolute magnitude always on the y-axis, but maybe at the left or right of the diagram. Okay. Right, now here's another one. Now have a look carefully at this. Spectral class is up the top. Still on the x-axis though. Your temperature in Kelvin is on the bottom. It's on the y, on the x-axis too, but it's on the bottom. On the left, you've got luminosity. On the right, you've got something called absolute magnitude. Now, absolute magnitude, we don't go into too much about it. You need to kind of be able to read the diagram. You're sometimes asked about absolute magnitude, but it's not very intuitive. So you get into -10 for a really bright star, okay? And +20 for a really dim star. So it's a little bit weird and it's a little bit counterintuitive. So make sure you identify whether you're looking at absolute magnitude or luminosity. Luminosity is easier to understand, but it is a log scale, what's known as a logarithmic scale. So you have to take some fairly intelligent guesstimates if you're looking at a star that comes sort of, down somewhere like here between 1 and 100, but that wouldn't be 100, it would be more like sort of 30 or something there. So you have to give an intelligent guesstimate there. So luminosity is it's easier to understand, but you sometimes get absolute magnitude in questions. So just be aware that the numbers are weird and do your best to work it out. But it's not a log scale, so it's probably quite easier to work out the answer. Okay, now notice there is a relationship between the place on the main sequence and the mass, and also the colour. So the red dwarfs are the lower mass stars, and the blue are the higher mass stars. So there's a definite relationship between place on the main sequence and the mass. Now, also notice that things like supergiants and that, they're not measured in mass so much because they are often bigger in size. The radius is bigger, but they're not more massive. The white dwarfs also. So it's just when we're on the main sequence, we're actually talking about mass. Right, and here's another one, much more complicated diagram, luminosity. On one side, no absolute magnitude, but you've got both spectral class and temperature in Kelvin down below. And another thing to learn here is that the redder the star, the slower that they fuse their hydrogen to helium, so the longer they live in it. And a massive star can live for up to kind of, possibly even 1 billion years or something like that. Whereas our planet will live for about 10 billion years, the red stars will be way longer than that. But the higher the mass, the hotter the core, the faster the helium is fused into hydrogen is fused into helium, and so you will get the really, really massive stars sometimes only living for about 1 million years or a bit more over 1 million years, because it's the live fast and die young stars. They burn their mass very quickly. They burn their hydrogen very quickly. Okay, so that is actually pretty much what I've gone over. So I'm actually going to go over that. They're far more red stars than other colours, but we don't usually see them unless they're giant red stars. We usually see white, blue, and yellow ones. That's what we're seeing in the sky. If we're seeing a red star like Betelgeuse, it's because it's at the end of its life, not that it's a red dwarf. Okay, now you can actually go over these explanations, and I really actually suggest that you do look over them and go back to a HR diagram. If you've got access to an old paper from your school, go back to the diagram that they tend to now use, but don't assume you will necessarily get that diagram. It is really important that you read all that stuff I said about the axes, just in case you were to actually get a different one. Okay, now stars and the fuels they use. The 3 fuels that a star will fuse are hydrogen, helium, and carbon, other elements, the 3 main ones. Brown dwarfs never start fusing hydrogen to helium. Red dwarfs, hydrogen to helium only. They don't form a red giant. Sun-sized stars, hydrogen to helium. Then when they've finished their hydrogen, they start fusing helium to carbon and oxygen when they're a red giant. That's all. They don't fuse anymore. Giant stars and supernova, hydrogen to helium, then helium to carbon, and then there's a whole lot of other fusion goes on until iron is formed. And when they get iron, that's when the star is likely to go supernova. So I've actually got that diagram in a table there, and that is also worth learning. Mate sequence stars are the most common stars in the sky, and I've kind of gone over that before. It's another way of presenting it. If you didn't understand the denser text before, then you might understand that better. And the same with all of that. Have a look at and make sure you actually know these different types of dwarf stars. They do kind of feature, and there was actually an exam question in 2020 where it was just talking about 3 dwarfs put together. So there's quite a difference between a red dwarf, a brown dwarf, and a white dwarf, for example. A huge amount of difference. They're in different parts of the HR diagram, and they have different properties. So you need to just go over that. Okay, now the birth of stars is common to all stars. So whatever type of star you've got, they are born in the same way. It's really just and by a collapse of a stellar nebula, which can also be called a giant molecular cloud. Make sure you know both those names. Stellar nebula is exactly the same as a giant molecular cloud. If a relatively smallish part collapses, that's probably going to be your red dwarf. But if a large, vast amount collapses, then that's going to be up in the kind of the blue stars, and somewhere in the middle will be our sun-sized stars. So now I've got some good diagrams on that, which hopefully, okay. So there are, yes, make sure, okay. So the space between stars are filled with dust and gases. These dark, enormous clouds called stellar nebulae or giant molecular clouds form from these. Stars are born in these. Gravity acts on the dust and gas, so not much gravity at first because there's not a lot of kind of matter. Then the more mass you get, the more it will attract by gravitational means more to form whatever size star it ends up being. These are absolutely vast and come from a collapse or only part of the nebula. So if you look at this diagram there on the left-hand tall column, you will see a little kind of almost looks like the ear of a dog sticking up. And further down, it's got a few of those. Those are probably where there are actually stars forming. And that's the Eagle Nebula. Okay, and that gives you a very good sequence. Nebula collapse, protostar formation. Pre-main sequence isn't always mentioned, but pre-main sequence is basically when the protostar is just at the point of becoming a main sequence star, which is when you get your hydrogen fusing to helium. Notice that all the way through this action of gravity, increase in density, energy changes are very important processes, and try and learn those if you can. So I'm not going to go, because of time, I'm not going to go over every single slide of these. These are good slides. They've got good diagrams on them. Make sure that you actually look at them. Here, this is actually showing that, of course, some of them within the actual nebula, there is going to be, obviously this is not just scale, but you're going to get clumps formed, and then the clumps are eventually going to clump together until there is enough mass for particles to rub together and generate heat. Heat, not fusion at this stage, it's heat through friction, right? You know the old friction thing. Do this and your hands get warm. So that's actually a process in stars as well. Okay, so there's more detail. Now, gravity causes collapse, contraction, and compression. I always used to say there's 3 COs: collapse, contraction, and compression of matter. This causes collision, another CO, friction, and heating up. Causes an increase in density. Gravitational potential energy is converted into kinetic and heat energy. This also starts to rotate, and this is called a protostar. It doesn't take very long, relatively, just 1 million years, or from 10,000 to 1 million years. Okay, now protostar to main sequence star. And basically matter just keeps on collapsing, keeps on generating heat or thermal energy and light. star, so these are starting to be dim and able to be seen. Density of the star is increasing. Heat is trapped, and the protostar eventually becomes opaque, weakly radiating heat and light. And a protostar with all its mass just before fusion starts is your pre-main sequence star. The main sequence star, the protostar, collapses, contracts, compresses enough so the core of the star is so hot that you're going to get thermonuclear reaction start, which is your fusion, which is your hydrogen to helium. Okay, so 4 hydrogen fuses to form helium with the release of a vast amount of energy. So you get a new main sequence star. Okay, and this main sequence star will be stable from until the hydrogen runs out, from 1 million to several billion years. What happens after that depends on how much mass the main sequence star has. Okay, so here I've actually put it into colour. I don't know why there's actually a red arrow diving down. I might actually have a look at that later. But notice that I've put the collapse, contraction, collision in yellow, anything to do with heat in red, and anything to do with density in blue. And that summarises it. Good thing to look after just before the exam, I think. Okay. Protostar radiates heat and light much like a fire or heater might. But thermonuclear fusion reactions are quite different and only start when vast amount of heat is trapped. They produce vast amounts of heat and light, unimaginably more than a fire would. Okay. Right. The formation of a protoplanetary disk, I've actually put this in here. This is also the start of the formation of planets, because as the protostar is collapsing, it rotates faster and faster. It throws out matter. So the protostar forms a central core. Don't get confused with the core from the middle of the star, but a central kind of bigger core, and a surrounding disk of flattened disk of dust called protoplanetary disk. And this is what planets and moons and comets and asteroids and all that sort of planetary solar system stuff will be formed. That's what it gets formed from. So I thought I'd put that there so that goes into your heads even while you're doing this. Okay, now these show jets being shot out from new stars. This just shows the instability of new stars. There's Matariki, also known as the Pleiades, and also known by many other cultures by other names. Young stars can be seen by gases around them, so you can actually tell that these stars are quite young stars. Lifespan, mass is important. I've been over that. Life and death of the stars, and there's kind of like two things. And this is a little bit tricky to get your head around, but, if you've got the headspace, do it. Going down to the bullet above the bullet point, what happens? Okay. Stars become main sequence stars after their birth. As their outer layer expands, the core contracts and become hotter because of increased pressure in the core. What happens after that depends on the original mass of the star. If the mass of the core at the end of the main sequence stage is less than 1.4 mass of the sun, a white dwarf forms. It is bigger, the star becomes supernova, and then a neutron star or a black hole. So you just if you can't get the hang of that, just remember a smaller mass is going to be your red dwarfs and sun-sized stars. A larger mass is actually going to be a supernova star. Now, there may be things going on in between. We're somewhere but on the boundary. Don't worry about any of that stuff. We just do the black and white stuff. This is your sun-sized star. This is your giant star, etc. Okay, so here's your type of main sequence star, stages, and this is actually worth learning, because when you get a question that is obviously going to be on the birth and or death of a of a star. Remember, the birth is common, but identify what the main sequence stage is. That's really important, that you identify what the main sequence stage is. And you can, and I would actually jot it down. So learn, sun-sized star, it's bored, okay, as I said, that's common to all of them. Sun-sized star goes red giant, planetary nebula, white dwarf, black dwarf. Learn it. If you've identified your question as being about a sun-sized star, that's the first thing you write down. And then you can worry about filling in text around it and explanations and what connects what. Okay, a huge star, you may get a smaller one or a bigger one, but about a 10 mass sun star is going to be supergiant, supernova, and neutron star and pulsar. And a pulsar is just a neutron star that's whizzing around really fast. A really massive star is going to be supergiant, supernova, black hole. Okay? So make sure you identify. The red dwarf stays as a main sequence star, only never becoming a red giant. I've never seen a question on a red dwarf about the life and death, and I doubt whether you get it, but make sure you know about it anyway. But definitely identify whether you have got a sun-sized star, which basically means it won't go supernova, or a supergiant star, which is going to go, a massive star, which is going to go supernova. Okay, really important. And here is a good diagram. This is the best one I could find, showing the life and death of the sun-sized star and a massive star in detail. So the bottom line is the sun-sized star and the massive one above. So, and there's another diagram. If you don't understand this one, you maybe have a one before, you can understand this one. Remember the structure of stars, I've been over that before. Red dwarfs, closest star to the sun, Proxima Centauri is a red dwarf. Red dwarfs form like other main sequence stars. They're the small stars, and they just literally go, when they've fused all the hydrogen, they become a white dwarf, and then they radiate all their heat away and they become a black dwarf. So that's red dwarfs. Sun-sized star. Now notice we are talking about mass of the whole star, not just the core. The core only becomes important when differentiating between ones that will go supernova and one that won't. So this is mass of the whole star. Right, there's the diagram. It's a little bit like middle age. That puts me pretty well on the end one, I think. Main sequence star fusing 4 hydrogen and helium to helium. There's a comparison between the sun as a main sequence star and the size it'll be as a red giant. It's going to cover way up to past probably Jupiter when this does happen in 4.5 billion years' time. Notice that the sun-sized star is running out of hydrogen. The core is contracting. A red giant forms and starts fusing helium to carbon and oxygen. So you've got the sun-sized star running out of hydrogen, and that's fusing, of course, hydrogen to helium. But in the red giant, helium becomes a core and ends up as carbon and oxygen. The outer layers expand and cool. The star is red because of the coolness, and it's very luminous because of its size. And you're often asked, why has a red giant got a high luminosity? Because if you look at it on the HR diagram, it's up on the right hand top corner. Its size, it's not more massive. It can't go more massive. The star is burning mass, right? It's fusing mass. Sorry, I shouldn't use burning. It's fusing mass. So this size is getting bigger. It's getting a bigger radius. The core is contracting, getting hotter and hotter and hotter, and it is actually fusing helium to carbon. And then once the red core carries on contracting, the star starts to run out of helium. There isn't enough mass in the core for any more fusion of any other elements. The core gets smaller and smaller. The outer layers drift cool and drift away, and you get these beautiful, beautiful planetary nebula forming. Okay, notice that it's called a planetary nebula, which has nothing to do with planets. Most of the star's mass goes into the nebula. The core contracts even more, and you get still will get some energy release. When all the helium has become carbon, the core becomes stable, since the core isn't big enough to compress carbon, which means it can't use carbon as a fuel. Then after that, what happens is the outer layers just float away. The inside layer becomes a white dwarf. No fusion is going on, but it slowly radiates away the heat until it becomes a black dwarf, which is just a cold lump of carbon. And there is actually one black dwarf which is even seemed to have actually, because it's all carbon, has formed some into diamonds. And if you know anything about the Beatles, it's called Lucy. Right, planetary white dwarfs. That's just what I've gone over. That's just repeating it for. Okay, notice now I've put where the red dwarfs and the white dwarfs are on the HR diagram, and I've explained it, and I'm not going to go over this because I'm running out of time to do the planetary stuff. But please note that that the red giants have got a high luminosity, although they're actually relatively cool, certainly the outer layers, because they're red. And notice the red giants are actually red, so therefore they've got to be cool, but they've got a high luminosity because they are so big in size that they have got a bigger radius. The white dwarfs have got a lower luminosity because they are so small, but they are much hotter because they've got all that leftover heat that they are gradually radiating away. And the white dwarf note is that's the core that is left. Okay, so that's where you find sun-sized main sequence on the H diagram, white dwarfs on the HR diagram. Explaining about red giants as well. They're right down the bottom of the HR diagram. I'm mixing up with red dwarfs here. There was something covering the slide. So red giants on the HR diagram, that's explaining that a bit more. Okay, and there's Sirius B, a white dwarf. And Sirius A is the much brighter one that we said, has got the highest apparent magnitude. Okay, this is extension only. I've never seen a question on ANOVA. Apologies if I've missed it and not just noticed it, but I would say the brighter ones of you read through that and try to understand it. Otherwise, don't worry about it. Giant stars, notice that's the mass of the whole star, not just the core. Excuse me, I've just got to bend a leg a bit. Okay, right. Life cycles of giant stars. A red supergiant, which is down. It's not actually showing the colour here, but it's Betelgeuse is at the bottom of Orion. Now we see Orion around about this time of the year from now on until kind of the late early autumn. We see it very easily in the sky, and it's quite a bright red or red-yellow colour. Supergiants now here, of course, they've got much higher masses. Their core, the same thing, their core contracts, their outer layers get bigger. Radius are not getting more massive, they're getting bigger with a bigger radius, but the core is getting hotter and hotter and hotter, and this means that not only have you got fusion of hydrogen to helium and then helium to carbon, but then you've also got carbon becoming a fuel as well. And so this is actually the same thing. The outer layers expand. They tend to be more orange-red than red-red, but they're still a cooler colour, but much higher luminosity, which will be explained in a minute. And then what you actually get, the fusion of elements. So the core is shrinking all the time. So in the teal is kind of the size of the core with the hydrogen helium. A smaller there's sort of a bit of a partial collapse, and you get hydrogen, helium to carbon. A partial collapse, but more than carbon to oxygen, oxygen to silicon. There's probably a lot of other reactions that go in. The most important thing, actually, is that hydrogen is a fuel, helium is a fuel, carbon's a fuel, and you end up with iron, and iron is not a fuel. Notice that the core contracts more each time another element starts to be made. For those who are interested, this just actually shows how fast everything goes. Iron atoms don't fuse. The outer layers of the giant star, outer layers of the core of the giant star gravitationally collapse towards the center of the star. This implosion happens very, very quickly. It takes about 15 seconds to complete. During the core, the nuclei and the outer parts are pushed very close together, so close that elements heavier than iron are formed. But iron isn't being used as a fuel. It's just that a massive pressure happens. And because that massive pressure, the nuclei are all pressed together. You know how the standard model of an atom shows you the nucleus with protons and neutrons, and it shows electrons around the outside. Now, all those electrons are squashed into the middle. Okay, so you don't get gaps. There's relatively a big gap between the nucleus and the electrons when we learn about atomic models. But those electrons get squashed down. So they're actually, in a way, the electron is squashing into a proton to form neutrons, and that's how you get a neutron star. So they're crushed together, and the core temperatures rise to about 100 billion degrees, and that's going to be degrees Kelvin, of course. The electrical forces between the atoms' nuclei repel each other, overcoming the gravitational forces, causing a massive, bright, short-lived supernova. Okay, let's see what the size is. And there's one that was in 1987 in the Large Magellanic Cloud. And now that brightness has gone, has faded, and in the middle is a neutron star. And this is just for interest. This is how all the elements are made, but you're not going to get a question on that. I think it's a really cool periodic table. Okay, so learn about if the mass is about 10 times the sun, you're going to get a small, dense neutron star, and it won't go any further than that. But if it's greater than that, you'll get something called a black hole, incredibly dense with a gravitational field so strong that even light cannot escape. Right, and I need to move on so you can read through that. Now, this is explaining about this on the HR diagram, so where why the supergiants are found out near the top. They've got a very high luminosity, but they're orangey red, so they're obviously cooler in colour. It's explaining that and shows where supergiants are too. Neutron stars and black holes aren't on the HR diagram. They have no luminosity. Brown dwarfs are found below and slightly to the right of red dwarfs, and they're not usually shown on an HR diagram. But you might get a question about them. Not a big question, but comparing them with something else. Okay, formation of planets and moons, and I've got 10 minutes. Right, so this is what we've just gone over. You've actually, and I introduced to you before, there's your nebula, there's your protostar being formed with a protoplanetary disk. The protostar is getting more dense. You finally get a main sequence star, which is going to be hugely brighter and hotter than the protostar. And the solar wind going out is starting already to sort of push matter out. And then what you actually get, and you actually start to get the formation of matter clumping together to form something called protoplanetesimals, and then you get planetesimals, and then you actually get the planets being formed. Now, going on, again, this is actually explained hopefully in better diagrams like before, except now you've got a protoplanetary disk, which is spinning. Remember that spinning, because that's why the planets are spinning in the direction that they do. And also, except except for Venus are rotating in the same direction as well. Okay. This shows protoplanetary disks around protostars. Particles of dust in the protoplanetary disks form planetesimals. Sorry, I had the name slightly wrong before. Planetesimals. When they're about 1 kilometre across, they start to attract each other through gravity, and eventually matter accumulates to form a planet. This takes something like about 10 million years. And here again is another diagram. I try to put different diagrams in so that if you don't actually understand one, you might understand another. When the protoplanetesimals started to get rather big, they started to collide with each other and collect to form planets. And then there was another stage, which I'll tell you about later. Now, this also is showing the protoplanetary disk. It's a slightly different shape from before, but it's still relevant. And this is showing from disk formation, dust sedimentation, planetesimal solid planets, and gaseous planet form. So the 4 solid planets, Mercury, Venus, Earth, and Mars, formed first, and then the gaseous planets formed after that. And you need to know that. Okay, now this is also a really important diagram because temperature becomes important. Distance from the sun and therefore temperature. And notice that it's in Kelvin. The disk is hottest close to the protosun and gets coolest at the edge of the disk. That's obvious, but make sure you've got it up here. The temperatures range from 2000 K, 1 astronomical unit from the sun, which is pretty hot, to under 100 K the further out you go. Now, this affects whether a new planet is a small rocky planet or a larger gaseous one. We'll keep on going. Now, what you actually have, now this is showing the protoplanetary disk in a slightly different shape, but it doesn't matter. You can see the planets forming. You have something called the frost line. Beyond the frost line, water can form ice. Inside it stays as a vapor in the formation of the planets. It was only rock and metals that were able to accrete and form planets in the earlier stages. The frost line is between Mars and Jupiter. Now, make sure you know the word accretion. Accretion means a condensing of matter under the influence of gravity to form larger bodies such as planets. So that's actually an important term. So rocky planets formed inside the gaseous planets, which are made of gases and water ice. They formed further out. Right, and this is actually showing it again, but in another way, where rocks and metals condense inside, outside, hydrogen compounds, rocks and metals condense. So your Jupiter, Saturn, Uranus, and Neptune, they all have got kind of little sort of solid centres, but then they've got a lot of kind of gas and water, and in some case kind of liquid hydrogen and things like that around them, and then are very gaseous, particularly Jupiter and Saturn on the outside, are more kind of watery and icy and gas with Uranus and Neptune. Okay, so that is explaining what I've already explained. But notice when the protosun becomes a proper main sequence star, the solar wind starts pushing matter away from the sun. And so that's where you will just get your heavier things kind of being able to form rocky planets. But the lighter stuff is all being pushed out to the outer parts of the solar system. Okay, you can read about the asteroid belt. I don't really have time. And also well beyond, on the asteroid belt, probably is something that didn't actually become a planet. But outside of the Kuiper belt are all the planetesimal kind of remnants that didn't either. And the Kuiper belt and the Oort cloud, now Kuiper belt is, Pluto's a Kuiper belt object, and there's other objects that meant that Pluto stopped becoming a planet because there's so many Kuiper belt objects that could potentially be planets too. It was easier to have the definition of a dwarf planet. The Oort cloud is even further on. Now, what's also important about the Kuiper belt and the Oort cloud is that the Kuiper belt has got what's known as short period comets, like Halley's Comet, that actually comes around every so number of years and can be predicted. The Oort cloud has what's known as long period comets, comets that suddenly appear in the sky and you don't even know they're coming, stick around for a bit and then go, and you don't know when they're ever going to come back. Now, collisions of comets with inner rocky planets probably help supply atmospheres and water to rocky planets. Now, there's a whole section here about, so the 4 inner rocky planets know these important points. They're small, solid surfaces, rotate slowly, have few or no moons. And this is how they were formed. Planetesimals attracted to each other by gravity. Denser material actually went into the core. The less dense went and formed the crust. Planetesimals kept bombarding the surfaces because there was still a lot of them around in the early days. You can still see scars of these on the surface of the moon and of Mercury. Atmospheres are formed around the planets with enough gravity to hold on to them. Okay, so that's a summary. The outer gaseous planets, much larger, rotate very quickly, mostly made hydrogen and helium, are very light, all have rings and many moons, don't have solid surfaces. We tend to see the tops of clouds. Pretty much the same thing happens as before, but this time you've got a whole lot more ice and you've got a whole lot more gas. But it's the same process, so make sure you look at these because I'm running massively out of time. Okay, the late bombardment, I've just talked about that right now, planetesimals that carried on. And you can see samples of these on Earth, and this is one was in Arizona. And Earth, of course, still gets bombarded, but we tend to see not very many actually land on planet Earth. Thank goodness, except when they destroy dinosaurs. Okay, gravity and the massive planets. I simply don't have time to go through this. You can actually read through this. You get a larger radius. I just simply don't have time. I would suggest that this is for the ones of you who are going for merit and excellence. I would actually put time into this. It would be part of an excellence answer, hopefully, rather than part of an achieve sort of section of an answer. Okay, now moons, 146 plus moons, only some are round. Some have been discovered around dwarf planets. Exoplanets will have moons. Only larger moons are round because it has to get to a certain number of planetesimals before it actually became round. Centre of gravity of a moon is the centre of the moon and all matter is pulled towards it. If enough mass around moon will form, if the mass is too small, moon stays lumpy shapes. 3 ways that moons can form: by collision, which is the moon, our moon, and Pluton's moon, Charon. Both moons are large, and Charon, large and relative to their planet. Moons that are formed from a circumplanetary disk, so much like planets were formed around a star, then the larger moons of the gaseous planet have got ones that were possibly formed in a very similar way, even though they're not around a star, they're around a big planet. Also, captured asteroids and Kuiper belt objects. These usually orbit their planet the wrong way. Now, that shows the formation of the moon. You can read through that, and that's actually got a very good diagram to show you. The larger moons, circumplanetary disk. These moons are close to Jupiter. They're dense and rocky. The 4 shown there. The further ones out, the ones we seem to know, Io, Europa, Ganymede, and Callista, are less dense and have more ice, except maybe for Io. That would be a pretty tough question to ask someone, so hopefully you wouldn't get that. I'd read over it just so at least you know about it, but don't put effort and don't learn all those moons. Okay. So that goes over how the larger moons of the gas giants were formed, and that shows a picture. Now here's Mars capturing its 2 moons, and so that's probably captured asteroids. It's kind of nicely diagrammed to show. Also captured Kuiper belt object. Neptune's largest moon, Triton, is possibly probably a captured Kuiper Belt object because it has retrograde motion, orbits the wrong way around. There are lots of tiny moons around the different large gas giants because they could very easily capture asteroids. Some of them haven't even been discovered. Every time a spacecraft goes out to the outer edges of the solar system, they find more moons. Okay, you can get major impacts. You just read these. There are a lot of things in here I suggest you just read through once and don't worry about again, but you never know when you're actually going to get a question. So there's actually Uranus is on its side because probably of an early collision. There is Orjo, that is Mimas. I always call that the Death Star. That's had a major, that's a crater from a major thing. You can get planets around other stars, and there was a question one year on planets forming around an exostar. Exactly the same principles as happen on our solar system is probably happening around exoplanets around stars that are obviously much further away from us. And here's the centre of gravity thing. You can actually look through this, and those of you who are wanting to understand it, that's explained there. Now, also, I'll just shut this down and stop sharing. Also, in your notes, which I haven't got here, because as you can see, I wouldn't have time to go through it, there is an extra PowerPoint that actually goes through the different planets. It is actually a really good idea that you have, that you know just about the different properties of the planets. It's because a specific planet may come up, and then if you know at least some of the properties of a planet, it means that you are not totally knocked sideways when you actually, if you get a question. I don't know what that's in the questions, obviously, but if you get a question. So I would go through that PowerPoint as well. Now, I do notice there were a couple of things I just need to correcting. I had Celsius instead of Kelvin a couple of times, and so usual thing, when you please come to do revision, refresh your screen, and anything that has been adjusted will pop up. Okay, so thanks very much and good luck for the exams. Hope you all do really well.
Lovely. Thank you so much, Jenny. Really appreciate that. Some awesome resources there. A few of the students did identify a problem with the link that was shared with them. The Google Drive folder, they can access the scholarship folder, but when they go to use any of the other folders that you've got organized by standards, it comes up with that the files, there's no files in that folder, or there's nothing available for them. I've had a wee look in the background, and the sharing settings seem to be okay from my end, but if I go in as a non-signed member, or if I don't sign into Google, then I can't access the resources either, which is quite interesting. So what I'll do is I'll put the link directly to the presentation, which works. And thank you, students, for helping me resolve that.
Yes, no, thanks very much. And I might have a look at that right now, even before I correct anything.
No worries. Whatever the settings are for the scholarship folder seem to be working, but it seems that the other folders don't work. And you can, if you wanted to go to, change it go in as a guest on a new browser tab, Jenny, you'd probably be able to see what I'm seeing as well, which is that the other folders inside that Google Drive that's been shared don't seem to be working.
So what is the best way of that? What is the best way? That might be because I don't need to sort of waste the students' time if they're still online listening.
I will. To me. I'll share the links to the presentations directly, and any other resources that you say, they really need those ones. Once I've done that, if you can you can have a look at the folders and see if there's a way to fix that for me as well. Yeah.
Yes, sorry about that. I possibly should check those. I've just been so busy, but yeah, well, I'll check those now. So
students, really appreciate your time and effort going into that. Awesome resources that'll hopefully help make a difference for them in the exam. So once again, thank you, Jenny. And as Jenny said, best wishes for your exams, everyone.
Yeah.
Ka kite.